Hi, today we're going to talk about stellar nucleosynthesis, the creation of elements. When I was a kid, my teacher told me that the sun, like all stars, is a ball of hot burning gas. Now I understand why people might say that, but it's an oversimplification that obscures a lot of truth. For one thing, the term burning to a chemist means combustion, a chemical reaction that involves combination with oxygen, and there's not that much oxygen in the sun. Second, the core of the star, where all the fun stuff happens, is made up not of gas, but of plasma. Now, why is that so important? In order to understand this, let's review the states of matter and how they look at a molecular level. So, remembering that all substances are made up of atoms or molecules, as a substance undergoes physical changes from solid to liquid to gas, these atoms or molecules are conserved. That is, they don't change into other molecules unless you also get a chemical reaction going. The way that scientists talk about these different states of matter is how high or low energy they are, but another way you can think about it is connectedness. The higher energy a state of matter is, the less connected the atoms will be. A solid is made up of molecules that are held together by relatively strong intermolecular forces. There are so many forces holding the molecules together that the solid can't change shape. A liquid is made up of molecules that are held together by fewer or weaker forces. So there's enough pull between the molecules to keep them together, but not so much that they hold their shape. In a gas, there are no forces holding the molecules together, so not only do they not keep their shape, they can expand or contract to fill more or less space. So what is a plasma? A plasma is an even less connected state of matter. With solids, liquids, and gases, no matter how connected you are, your atoms are conserved. That is, one type of atom doesn't change to another sort of atom. But in a plasma, things are so disconnected that not only do molecules come apart into their component atoms, but atoms actually come apart too. Before we look at how that happens, let's take a little detour and think about the structure of an atom. Remember that the number of protons in an atom is what gives that atom its chemical properties, and therefore determines what sort of element that atom is. Neutrons affect the mass and nuclear stability. And both protons and neutrons are clustered in a tiny area in the center of the atom called the nucleus. Electrons are much tinier than protons and neutrons, but they also occupy the remainder of the volume of the atom, not because there are a lot of them, but because they move so quickly. Electrons are what help connect atoms to each other, but importantly, they also keep atomic nuclei from getting too close together. When it comes to electrical charges, charges that are different attract, while charges that are alike repel each other. The molecules on the outside of my hand have electrons on the outside, and those electrons have a negative charge. The molecules on the outside of this table have electrons on the outside, and again, those have a negative charge. So when I push my hand against the table, the electrons on the outside of both things repel each other. It's why we'll never be able to walk through walls. So now let's go back to plasma. A plasma is such a high energy state of matter that the electrons of an atom actually disconnect from the nucleus. So you end up with this very high energy soup of electrons and nuclei moving independently of each other. And this is why we get what we call stellar nucleosynthesis. Nuclei smash into each other at a very high speed. And because nuclei in a plasma have no attached electrons, there's no repulsion keeping them apart. Again, the plasma is at a very high energy, so all of these particles are moving super fast, and two nuclei may collide and remain stuck together because of the speed at which they collide. When that happens, the number of protons in that new nucleus has changed, and it therefore changes into a completely different chemical element. So the universe began as a set of unconnected protons and electrons. And it's this process of stellar nucleosynthesis that has changed those into all the elements we know today. But stars don't create every element equally. And this is what I particularly want to talk about today, because it turns out that the elements that are the most abundant are the ones that will affect what life will be made of. So let's look at what sorts of elements are made in large quantities in stars. Now let's start with an extremely young star, one whose plasma is wholly composed of single protons, single neutrons, and electrons. And putting aside electrons for a while because those won't affect what elements we get, let's think about what we would get if a proton and a neutron collided. A simple balanced nuclear equation tells us that you will get a hydrogen atom with a neutron, what many scientists call deuterium. This is sometimes written with the symbol of D to represent deuterium. The other thing you'll notice in this nuclear equation is this gamma symbol here. That represents a gamma ray, a high energy photon. It's important to understand that this process produces energy. In fact, most of the reactions I'm going to show you today produce a lot of energy, but I'm going to leave off the gamma rays for simplicity's sake because we're only talking about the elements. Okay, so now we have neutrons, protons, and deuterium in our nucleus. What sort of things could collide in that plasma? Well, we could have deuterium colliding with a proton, which would give us helium-3. We might also see deuterium colliding with deuterium, which might give us a couple of different things. The reason this happens is that when you have larger nuclei smashing together, sometimes they form one thing, and sometimes they fragment into one larger and one smaller particle. So for example, two deuteriums can combine to form hydrogen-3 and a proton. Hydrogen-3 is also called tritium, so the isotope symbol is sometimes written with a T instead of an H. Another possibility is your deuteriums can smash together and form helium-3 and a neutron. Now we can add tritium and helium-3 to the list of nuclei swimming around in our plasma. So what sorts of reactions can we have now? Well, tritium and deuterium can combine to form helium-4 and a neutron. Or helium-3 and deuterium can combine to form helium-4, what we also call an alpha particle, and a proton. You might ask, why tritium and deuterium? Why not tritium and helium-3, for example? The answer has to do with the probability of collisions. So you might want to think back to the kinetics chapter of general chemistry, to the idea we call collision theory. In a nutshell, it's this. In order for a chemical reaction to happen, two molecules need to collide with the right energy and at the right angle. And this leads to all sorts of explanations linking the probability of collisions happening to the speed at which the reaction occurs. One of the takeaways is that the higher the concentration of something you have, the more probable it is that that particular thing will react. The higher the temperature, also, the more likely you are to get an effective collision. Now, obviously, stellar nucleosynthesis is not quite the same. We aren't doing chemical reactions here, and collision angles don't matter. But the more concentrated a particular isotope is, the more likely it is to collide with something to get a fusion reaction going. And the higher the temperature, the more reactions you will get because you're going to have more high energy collisions. So now let's look at what happens as helium-4 starts to build up in a star's core. At first, it can make things like lithium-7 if it combines with tritium, or beryllium-7 if it combines with helium-3. But as you get a higher and higher concentration of helium, you're going to get more and more and more helium-4 reacting with itself or other products. You can get helium-4 colliding with itself to form beryllium-8. You can get helium-4 reacting with beryllium-8 to form carbon-12. And you can get helium-4 reacting with carbon-12 to form oxygen-16. Now, two notes at this point. First, these aren't the only reactions that are happening. You're still going to have a bunch of protons in your plasma, and so you can get things like the CNO cycle, shown here, going on. This cycle does happen in our sun, and one thing you will notice is it keeps a reasonable amount of carbon, nitrogen, and oxygen present in a star like our sun, and that's going to be pretty important later. Secondly, you have to think about nuclear stability, and this is why it's so important to look at the chart of the nuclides. Going back to this slide, we see that beryllium-8, which is produced here as a precursor to carbon-12, is not very stable. Looking on the chart of the nuclides, we see that it's colored red, which means it has a half-life of nano to picoseconds. So basically, to make carbon-12, you have to get two helium-4 nuclei, remember also known as alpha particles, to collide and then have a third alpha particle hit it almost immediately after. This reaction, known as the triple alpha reaction, will only happen in large quantities when a huge proportion of your plasma is composed of alpha particles. So the triple alpha reaction will only happen when an average sized star is pretty old, or after a reasonable period of time in a larger star. As a star starts to generate lots of carbon and oxygen, it could fuse these to create heavier elements. Note that this only happens at higher temperatures. Remember, nuclei have to hit with enough speed to fuse, and the larger the nucleus, the higher the temperature it will need to reach a given speed. So here we see two carbon-12 molecules colliding to form a number of possible products. Neon plus an alpha particle, sodium plus a proton, or just magnesium. We could also have oxygen 16s colliding. This will give us elements such as silicon, phosphorus, and sulfur. But in the last day or so of a large star's life, it starts to fuse silicon, a process that is rather unique. First of all, at these super high temperatures, which are around 3 gigakelvins, elements undergo a process called photodisintegration, where they are breaking down and giving off protons or alpha particles. So suddenly, in this plasma, where you originally had a bunch of carbon, oxygen, silicon, and whatever, you now also have lots of protons and alpha particles around. And these alpha particles start slamming into things, very high temperature, right? And making bigger and bigger elements. Now, I've skipped a bunch of steps here. You wouldn't actually have 7 alpha particles colliding with a silicon at the same time. But the important thing to know, to take away from all this, is that iron 56 has the highest binding energy of any atom, and you literally can't get any more energy out of fusing elements higher than that. Any other fusion reaction past iron 56 is going to be endothermic. In other words, you have to put energy in. Now, as you've heard on a previous video that I had you watch, supergiant stars die by exploding in what we call supernova. The energy of this explosion is big enough to cause even heavier elements to be synthesized through fusion, and it's that which gives us all the rest of the known elements. So in summary, what we expect to see the most of in the universe is what we get from average-sized stars the size of our sun, lots of hydrogen, helium, and a bit of oxygen, carbon, and nitrogen. We also expect to find a reasonable amount of what larger stars make: neon, sodium, magnesium, silicon, phosphorus, sulfur, iron, and nickel. Now I want you to look at the most abundant elements in the universe: hydrogen, helium, oxygen, carbon, magnesium, and silicon. All of those are found in the lists that I gave above. Consider the most abundant elements on Earth: iron, oxygen, silicon, and magnesium. Again, these are all found in that list of elements commonly made by stars. Planets will primarily be made of the elements that are most abundant in the universe, and so will life. Life as we know it is based on the 6 elements we call CHNOPs: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And again, these are all found in the list of elements that we've talked about today that are being produced by stars in large quantities. So, stellar nucleosynthesis may have seemed like a strange thing to begin an astrobiology course with, but it is absolutely crucial. We have to understand what elements are available in large quantities before we know what life will be built out of. So I hope this was helpful, and I look forward to seeing you again soon.